Illustration number 8. A particle of mass m is placed on each vertex of a square of side L as shown in this figure. We have to calculate the gravitational potential energy of this system of four particles. And here you can see the four particles are situated at point 1, 2, 3 and 4. So first of all we will try to find out potential energy and then we will find out the gravitational potential. And here we can write down the gravitational potential energy due to every pair of particles. So which are the pair of particles? So general result first of all I am writing the gravitational potential energy for the pairs of particles is given by this equation U subscript ij, where I and j shows the pair of the particles, is equal to minus g mi mj divided by rij. So this is equation number 1, and here mi is the mass of ith particle, and similarly mj is the mass of jth particle, and rij is showing us the distance between ith and jth particle. Here I am considering that all are having the same mass. Therefore, instead of writing mi and mj, generally I am writing small m. And therefore, the total potential energy which I will get is denoted by capital U is equal to minus g m square into the bracket summation over I, and remember that you have to consider I is less than j for the distance should be positive, 1 over rij. So such kind of pair we have to obtain from the figure, and it is very easy because it is only for 4 particles. So U is equal to minus gm square into the bracket 1 over r12 plus 1 over r13 plus 1 over r14. From the second particle, it is 1 over r23 plus 1 over r24, and the last one is 1 over r34. In these all cases, you can consider this I values is always less than jth value. And now we can find out the values of 1 over r12 and r13 respectively. Therefore, U is equal to minus gm square into the bracket. Now R12 is L, so 1 over L plus R13. So here they are vertically opposite to each other, and so I have to use one triangular law for vector addition. So it is R3 minus R1. And finally the answer what you will get is under root 2L. And from where does it come? I am giving you. R13 is equal to R3 minus R1 is equal to what you will consider in this way. Under root 1 square plus 1 square into L is common. So mass I am considered over here. So it is under root 2 into L. So similarly R13 has been obtained. Now R14. So it is also very easy to find out because it is in the same plate. Now R23 is also in the same plate, so it is 1 over L plus R24. Now they are vertically opposite, so again it is under root 2L plus R34. They are also on the same plate. Therefore, U is equal to minus Gm square into 4 times 1 upon L. So it is 4 over L plus 2 times 1 over under root 2 into L. Therefore, U is equal to minus Gm square into the bracket 4 over L plus under root 2 over L, because 2 is cancelled by root 2 and the remainder is under root 2. Therefore, U is equal to minus Gm square and here 4 plus under root 2 divided by L. Now, the gravitational potential, so this is the total, but we have to find out the gravitational potential at the center due to each particle. So this is our first result what we have obtained. Now our next task is to find out the gravitational potential at the center due to each particle is same. And now the total gravitational potential of this square at the center that means phi is equal to 4 times potential energy due to every particle. And so I can write down 4 into minus Gm into 4 plus root 2 divided by L. And I am taking this 4 plus root 2 divided by L as minus Gm over R. So it is, I am taking 1 over R is equal to minus 4 times G into M over R. And if you more simplify this result, then you will get this answer minus 4 under root 2 G into M over L, where this 4 times I have cancelled out. So root 2 over L, so this will be cancelled, 1 over L. So it is only root 2 over L, and hence this is the actual value of gravitational potential. And now we will see some another kind of approach, that is escape speed and escape energy, in our next class. Illustration number 9. For an object lying on the surface of the earth, the escape speed is 11.2 km per second, which is the general escape speed for any object of the earth. Now, if an object on the earth is thrown away with a speed 3 times this value, so the initial speed is given to us. The initial speed of an object I am denoting it as simple V is 3 times the value of VE. So is equal to 3 times 11.2, that is not 66, it is 33.6 km per second. Now, with the use of this, suppose the speed of this object after it escaped from the Earth's gravitational field is V dash. So the speed of an object after escape from the Earth's gravitational field so I am considering this speed as V dash, and now according to the law of conservation of mechanical energy, we can conclude one thing, that the kinetic energy plus potential energy at the Earth's surface is equal to the kinetic energy plus potential energy at infinite distance. So both will be equal. And here, if you see the kinetic energy plus potential energy, so what will be the kinetic energy? It is half mv square plus the potential energy is minus g mass of earth into mass of the body divided by radius of the earth. And on the right hand side, only kinetic energy will be affected and the potential energy will be 0. And so I can consider that here the velocity will be after escape from the Earth's gravitational field, so it is V dash. But we know one thing, VE is equal to under root of twice GME over RE. So what happens if I square on both the sides? Therefore, VE square is equal to twice GME over RE is equal to, now what I am doing, I am making this GME over RE as an object because it appears in the law of conservation equation. So VE square divided by 2 is equal to GME over RE. Now I am substituting this result number 2 in result 1. Therefore, half mv square plus minus GME over RE. So it is minus VE square by 2 and into there was a multiplication of m and the right hand side is as it is, that is half mv dash square. Now we have the value of small v is equal to 3 times VE. Therefore half m into 3 times VE whole square plus minus VE square m by 2 is equal to 1 by 2 m v dash square. Now what I am doing, see, this is half m from here, half m from here and half m from the first term I am getting cancelled out. And therefore my equation will look like 9ve square minus ve square is equal to v dash square. Therefore here 8ve square is equal to v dash square. Now taking square root on both the sides, then this is under root of 8 VE is equal to V dash. And that was our target, to find out the velocity or the speed after it was escaped from the Earth's gravitational field. Now what is the value of VE? It is 11.2 and therefore under root 8 into 11.2, so the answer will comes out to be 31.63 kilometer per second. So see, the velocity after escaping the Earth's gravitational field is very higher than the escape speed. And so this was our conclusion from illustration number 9. And now we will switch on to the next illustration.